thing that we're going to do, and this is the last problem for this level, is calculating equilibrium pressures and concentrations. Okay, to make this video shorter, because I know it's kind of long, I did not include an example on how to calculate the equilibrium pressures, but you may have a problem, number 43, on your homework assignment that has you do this. And so I would look at page 623 in your book, example 13.8, and this tells you how to do it there, okay? But if we know how to do that, then, and if we see what we're doing here, that will be helpful for you. So we're going to do the calculating equilibrium concentrations instead. So sometimes we aren't given any concentrations or pressures, only initial values with the zeros. And so we have to figure those out. We're going to use the stoichiometry of the reaction, and we'll use what's called an ice chart to show the changes in concentration. Okay, so for example 7, you need a lot of room, okay? So I knew that there wasn't going to be enough. So if you look on page 9, there's a whole bunch of space. I used up that entire space on page 9, along with the entire bottom space on page 8. So here we go. Carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. At 700 Kelvin, the equilibrium constant is 5.10. Calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. All right, so the first thing we should do is write our balanced chemical equation. Okay, so we have carbon monoxide gas reacting with steam, so that is water vapor, gaseous water, to produce carbon dioxide is going to be a gas, plus hydrogen. So that's hydrogen gas, H2, so it's gas. So now that we know it's all gases, we're going to have to include everything. Okay. The next step is we need to figure out the initial concentrations, because we're not given those. Okay. So to find the initial concentrations, we are told that all of the species have 1 mole put into the 1 liter container. So moles per liter is molarity, so we can solve that out. So the concentrations will all be equal to each other. All of the initials will be equal to each other, which is nice for our math. So again, remember that if it has a little 0 at the bottom, that means initial concentration. And so to find the initial concentration, since all of them have 1 mole added to a 1 liter flask, all of them will have 1 mole per liter, or 1 molar concentrations for their initial concentrations. Okay? Once we know the 1 molar concentration for each one, for the initial concentrations, then we're going to set up Q. Because if Q is equal to K already, then we are good to go. We don't have to do any of this math. Okay? Because we said in the problem that K is 5.10. So let's compare. So our Q will be products of our reactants. So the CO2 times the H2. I didn't point it out, but it is balanced already. So we don't need any exponents for us today. So we can plug in our 1s. They're all 1. And I'm going to save space by just putting 1 without all the decimals. But if it's 1 times 1 over 1 divided by 1, or 1 times 1, then that all equals 1. So comparing our Q to our K, Q is less than K. So that means that we will have to shift to the right to make more products. This is going to be important in our ice chart. Okay? We always shift. We have to know which way we're shifting so that we know where we're adding and subtracting on the change line. Okay? So next we need to set up our ice chart. This is where I flip to the other side, if you have any other. So we're going to set up our ice chart. I stands for initial, C stands for change, and E stands for equilibrium concentration. So this is initial concentration. So if you want to put for concentration, and then E is equilibrium concentration. And we have to do this for each part of the reaction. So I had to rewrite my reaction up above. Okay, so on the initial line, we said that the initial concentration of each one was 1 molar. So, excuse me, so each one of them will have the 1 molar concentration to start. Okay. C stands for change. How does the concentration change when equilibrium is reached? Okay, and this is where that shift is important. Because we said that we are shifting right before, that means that we're shifting towards products. So our change, we're going to just use a value of x because we're going to solve for x, okay? Since we're shifting to the right, we're losing concentration from the reactants and we're gaining concentration from the to the products. So that means we have to subtract our change from the reactants and add our change to the products. Okay? The only thing that would be different, maybe in your homework, would be, in this case, we all have just 1x on everything across because everything has a coefficient of 1. But if you had like 2H2O, that's when you would have a negative 2x, or you would have twice as much. Whatever the coefficients are, they come down to be with the x. Okay, that's where the only part I don't like about this example. Okay, and so then after we know our initial and our change, then we can figure out our equilibrium concentration and what that would be. So for the change, you add them together. So for the equilibrium concentration of the CO, we would have 1 minus x. I'm just going to save space by not putting those zeros, okay? Same thing goes for the water, where we have 1 minus x. But then, when we get to the CO2, now we're adding the x, so it's 1 plus x, and for the H2, it's 1 plus x again, okay? So now, when we get these concentrations at equilibrium, we are going to plug into the K expression, because we know K was given in the problem, and we have to solve for x, because that will get us our equilibrium concentration at the end. If we know x, then we can just plug it in right here and solve for what everything is. Okay? So our equilibrium concentration, our equilibrium expression, products over reactants, we plug in that like 1 minus x or 1 plus x in the right spots. We know K from the problem was 5.10 equals, and then each of the products were 1 plus x. So 1 plus x times 1 plus x over, and then we had 1 minus x times 1 minus x. Okay? Well, to simplify life a little bit, I'm going to pull, since they're multiplying, so it's really just each of them squared, quantity squared. Okay, and then if we have it squared, then to get rid of the square, we have to just take the square root of both sides, so then we can cross out our squares. So the square root of 5.10 is a decimal. I just rounded it to 2.26, which is fine for us, equals our 1 plus x over 1 minus x. So now we need to do some algebra. We're already doing algebra, but yeah. So we need to multiply both sides by the quantity 1 minus x to get that out of the denominator. Okay, so we have 1 plus x is equal to, distribute this through, so we have 2.26 minus 2.26x. So now we have to get the x's on one side and numbers without x on the other side. So I'm going to subtract 1 to both sides, and I'm going to add the 2.26 just to make it have a positive x. So our answer comes to us faster. So we now have 1.26 is equal to, so these cancel, 3.26x. So then to get x, we divide by 3.26, and x is equal to, I rounded, 0.387. This is not our answer yet. So now that we know x, we can go back to the equilibrium line, this line right here, and figure out what that concentration is. So for each of the reactants, the concentration of the CO equals the concentration I don't know what it's doing. So the concentration of the CO is equal to the concentration of the H2O, because they're both 1 minus x, right here. So to find what those concentrations are, we take 1 minus the x that we just solved for, which is 0.387. So both of those guys equal 0.613 molar. And for the products, both the products will equal each other. So in this case, we add 1 to our x. So we get 1.387 molar. I will do one of these in class with you guys so we can see how to do this again. It's a lot of work, I know, but now we're done. So you have for problems to do for level 59, 33AB, 43, 51, and 52.